all the time trying to like apply makeup. There's that slight delay with their phone. They're like,
Apparently, doing that kind of stuff is banned on New York City subway.
yeah, exactly. That's what I was just saying.
That's right. Kind of
Okay. So I'm happy to introduce Percy Liang today. He's our first CLS series, like talk series speaker here. And he's an assistant professor at Stanford right now since 2012, technically. And he has done an amazing job on like statistically modeling natural language and basically semantic parsing that we will hear more about today. And so I'm happy to.
Great, thanks Nazrin for inviting me, and thanks everyone for coming. So generally, I'm not a cognitive scientist. Let's just start with that. And so most of the time I spend my thinking about how to build systems that can understand language. But I think some of the models and algorithms that I develop could potentially be of interest. And I'll try to point out connections where, maybe from a cognitive perspective, some insights could be gained. So one way you can think about the work I'm going to present is from this following question. Can a system learn linear representations from behavior in a computationally efficient way? And the things I bolded are the two things I tend to think a lot about. Learning from examples and what does it mean, when can you do it, and also an eye for computation, because real systems have to be reasonably fast. So maybe here's some three things I thought we should kind of keep an eye on during the talk. So when we're doing this kind of engineering effort, there might be new phenomena that actually occur, which might not occur in kind of a maybe more laboratory setting. There's kind of new computational and statistical tools which could be useful for modeling cognition. And this also, when we present a system, we can think about it as an artifact or a data point that suggests this can actually be done from this amount of data with this computation. So maybe that could reveal something more universal about how learning and language work. So let's begin. I guess one thing that's, I don't have a great mental model of what you guys know or don't know, so feel free to ask lots of questions. I think we're a small enough group that we're happy to make this interactive. And if you get bored or something with some section of engineering details, feel free to yawn. All right. So here's kind of just to give you an idea of what's kind of the way I think about approaching these problems. Suppose you're interested in climate change, and I want to build systems that can help you understand what's going on, and in the form of natural language understanding. So you might ask, which country has the highest CO2 emissions, which had the highest increase since last year? What fraction is from the 5 countries with the highest GDP? And so I'm put these questions up because they require aggregation and computation. So it's unlikely that you can just answer this by looking up some web page. You have to know where countries are. You have to know what GDPs are. Compute the highest, take the 5, and then look at fractions. So it involves actually some arithmetic even. So these are type of the kind of questions we're interested in. And I'm going to do it, kind of keep that end goal in mind, the end-to-end goal of building the system to do question answering. And then I'm going to figure out, let that end goal drive the intermediate representations that we're going to learn. Okay, so just to set the stage. So this idea of question answering on databases has been around since, let's say, the 60s. Generally, the systems were rule-based in the narrow domain. On the other hand, you have Google search, which doesn't really understand anything, but it's extremely useful nonetheless. So you can think about these two techniques as being kind of opposite end of the spectrum. One is very broad and deep, and one is deep but not very broad. And so in recent years, the thrust of my research has been trying to be down here. We're not there yet, we're probably around here, but the goal is to develop these semantic parsers which have the rich understanding, but trying to scale them up to more realistic settings. And I think the scaling up is, you should think about this not as just, oh, we're going to toss more data and handle, just oh, we did something here and we're just like scaling it up. I think there's actually genuinely new challenges that appear when you're actually looking at more realistic settings, like lexical ambiguity becomes a much larger issue, which is real. So the paradigm that we're going to think about is semantic parsing, which is taking a sentence, a question, and mapping it into some sort of logical form, which you can think about also as a program or a database query, such that when you execute this, you get the answer you want. Okay, so that's the framework. And so now let's talk a little bit about what this intermediate representation is. So some of you probably taken semantics and seen logic. Well, actually, how many of you have know what Montague semantics is? Okay, so so let me explain a little bit. So traditionally, semantics is the process of taking sentences and trying to represent them as some sort of logical form, typically in first order logic or calculus or something. And generally, this is done compositionally. I'm not showing the composition here, but this is the end result. And here you can see that there's a predicate visited taking two arguments, Percy and Rochester. But actually, in practice, what we deal with is not examples like this, but things which are more complicated. And to give you an example, here is a reasonable way to interpret how many people live in Seattle. You take a set of people, a set of things that live in Seattle, you intersect them, and you count how many other things are in the set, right? But if you're trying to build a system to answer questions, it's actually not that simple, because in the database that we're going to use, actually population happens to be expressed as a relation. And so you need to somehow map how many people to population now, which is not exactly what you do in classical semantics. And worse, you have to know that this population is in the year 2015. When that 2015 doesn't show up, where does it come from, and so on. So in some sense, what we're talking about is high-level language mapping to these lower-level logical forms. So, and that's kind of one of the key challenges in understanding language, is that it's these predicates like live in Seattle or how many people aren't necessarily the things that are the primitives that you want to know about. Okay, so I'm going to talk about two projects. In the first one, it's basically the goal of this is really to lay out the technical framework, and this is going to introduce the main tool, which is log linear latent variable models, which we found to be extremely useful for handling these in a reasonable computational time. So this is work with Jonathan Barrett, Andrew Cho, and Roy Frostig that we've been doing over the last 2 years. So here is a framework. So if you know what a Bayesian network is, this is a Bayesian network, and if you don't, it's okay, because it's basically, you can think about it conceptually as describing how the dependencies between the various components interact. So here we have a sentence, and we're going to think about a model that places a distribution over logical forms, conditioned on the sentence and some parameters. So we're going to do things in the kind of the conditional world. So we're not going to have distribution of the sentences, we're going to condition on them. Mostly because in practice we observe them, so we're not going to spend time modeling them. Okay, so given an utterance, we have a database of facts about the world, and you run a database query on this database, and you get an answer. Okay, so that's the schema, and the nodes which are shaded are the things we observe as we train them. So remember, we're going to learn stuff. So what does our training data look like? We have database, we have question answers. But we don't see the logical form of that. So this is why, when I said, learning latent representations from behavior. So I can think, of X and Y as kind of behavior in the sense that if you're actually talking to someone, you have question and answer exchanges, but you don't actually, look inside their head and see what logical form they have. So, Okay, so I'm going to go through the different components of this model. So the first is the database, and for question answering, we use something called freebase, which you can think about as a large directed graph where nodes are entities and edges are relations. So this says that Barack Obama was born in 1961, he was born in Honolulu, Honolulu's open, and so on. More generally, you can think about the world, or the database here, is really the context in which you understand a sentence. So for example, and we do this in other work, where if you're in a room and you're trying to control a robot, this graph actually corresponds to the objects in the room and their spatial relations. So think about it more abstractly than the concrete database here. So the logical forms we use is something called Lambda DCS, which we developed. And the basic way to think about it is basic Lambda DCS expressions denote a graph pattern, such that an execution means matching that graph pattern on the graph, which results in a set of nodes. So this is nodes which are high people and places of location Chicago, and that matches Michelle and Barack. So that's kind of, it should be your intuitive view. More formally, Lambda DCS is defined as any language is defined recursively. So you have entities like Chicago. You can do a join, which corresponds to following an edge on the graph. So you can get the people who were born in Chicago. You can take two sets and intersect them, and that does the natural thing. You can aggregate using count. You can take a set and then look at a particular property, which maps elements of that set to a number and do argument argmax. You can do a NAFRA where this is people whose children influence themselves. Right? So here X appears here and also there. And finally, you can learn kind of more abstract things like gender, female, intersect with children. Children is grandmother. And so this is kind of the language. And some of you probably have seen lambda calculus, and just to briefly comment about what are the differences here. So lambda calculus, to express people who lived in Chicago, this would be the lambda calculus expression. And the main thing that lambda DCS does is tries to simplify things by removing the variables. And in doing so, you have to, this variable is existentially quantified, so we notice that often in practice, things are generally existentially quantified, so we just make that as a default. And you can intuitively think about, if you think about Boolean logic, right, you're thinking about operating on Booleans, intersection, and or. Basically, what we're doing, the way to think about lambda DCS is operating on sets via intersection. So it's just kind of a lifted operation. And this turns out to be quite natural for natural language because if you think about it, a noun phrase kind of denotes a set of things, or a noun denotes a set of things, and it's much easier to compose sets when we're not worried about the variables set. And this is inspired by some other discourse representation theory within linguistics, which has similar properties in the sense that they have extended modification.
Negation?
We have negation. They're not. I guess I forgot negation, but yeah, we have negation. That's a good point. Okay. So now we have know what the world is a graph. These logical forms are essentially graph patterns augmented with things like argmax. And now we're ready to proceed on the problem of mapping natural language to actual logical forms. So the way we do this is using a grammar that takes an utterance and generates a set of candidate derivations. So the purpose of this grammar is not to, in the linguistic sense, model what is grammatical, but rather in the computer science sense to just specify a set of things. So here's something, so we generally use very simple grammars where you can think about them as having like 20 rules. utterance. So here's an example of how you would use a grammar to produce a logical form given an utterance. So you build a derivation tree where leaves are the words in your sentence, and each internal node corresponds to application of a grammar rule. So you have lexical rules like mapping live to places to live location, and then you have composition rules like join and intersect. Okay, so this is one particular derivation. It happens to be the correct one, but you could have also applied other rules. And for example, you could have gotten or organizations in Chicago music or something, or many others. So generally, there's like thousands of derivations. But so the question now is, how do you actually score these derivations? So let's zoom in on a candidate derivation and on the utterance. So those of you who have seen kind of basic machine learning like classic logistic regression or SVMs, this is kind of the structured generalization of that. And the idea is that, so we want to map utterance to derivation, right? So we're going to have to score each of these somehow. And the way we score it is, why is this a good derivation as opposed to some other one? Well, it's good because, parts of it are good. And the way we kind of get a notion of parts is via a feature vector. So you can think about a feature vector as taking a pair and chopping it up into little bits, where each bit you can think about as a pattern that is generally can be associated with either good or bad. So for example, this one says, did you just lived mapped to places live location? So a priori we don't necessarily know if that's good or bad, but in the end we hope that it's good. Live maps to place of birth, that's probably bad, right? So we have a bunch of features which think about it as a set of, if it's convenient, just think about these as 1 or 0. So these are a set of patterns. And the way we actually get the score is basically each feature has a weight associated with it. Positive weights are really good, negative weights are it's bad, and then we take a weighted combination of the features. So here are the features, it's just a feature vector, and there's a weight, you take the dot product, you get a number. High scores are good, low scores are bad. And then to actually construct the model, you, because probabilities have to be positive and sum to 1, this is kind of a standard thing where you exponentiate, so you get a positive number, and then you normalize, so you get something that's close to 1. And the normalization is summation over all the possible derivations generated by the grammar. Okay, so this model is, this is kind of bread and butter stuff in NLP, but we're kind of applying it to this, perhaps more interesting, semantic processing. Any questions about this so far? Yeah.
So I assume that in some cases you can have infinitely many derivations for instance. Does that happen even now?
So in practice, the way we construct the grammar is it generates only a finite number of derivations, but that could still be very bad. It could be exponentially large. So in practice, we prune. And I'll talk a little bit more about that later. Okay.
About the feature vector, is that just all by hand?
Yeah, so good point. So the feature vector is defined by, let's say, about 20 feature templates, which are written down by hand. So a feature template corresponds to saying, some word maps to some predicate. That's one feature template, and it gives rise to, in that case, like 100,000 features or something.
So how many total features do you have?
So it could be, 10,000 or more. Generally, whenever you have these lexicalized features, so it's kind of confusing in the literature. People will say features when they really mean feature templates. Like these features, this is like one line of code, and that's kind of a feature template, but it gives rise to like 10,000 features, with each of which has a weight. whereas something like I know alignment score is like one number, and this is actually more than one number. So okay, so let me go on. So one kind of conceptual point, maybe this is kind of a broader takeaway, is that language is really complicated. And if you were trying to actually define a grammar that captured all the aspects of how language works, you would end up with something very complicated. So instead, what we do is we kind of relax and say, we're going to just generate an overapproximation for derivation. So instead of making sure that this point stays out of the set and this point is in the set, we're just going to say, let's just find some coarse rules and generate derivations which might not be, some of which might be wrong. And then the philosophy is that we're going to rely on machine learning to, based on data, and the features to basically score everything in the set, and that'll actually give us a much richer way to think about, to carve out this boundary. And in particular, it'll give us actually probabilities, the distribution over the set rather than just a hard set, which is hand-coded. So if you can think about this as replacing the hard grammar rules with soft overlapping features, which is, I think this modeling, thinking in terms of these features from a modeling perspective is really powerful because it gives you the flexibility to put in different types of domain knowledge, and you don't have to have necessarily like a coherent view on, coherent view of how everything integrates. So definitely from a practical point of view, this is quite powerful. Okay, so just to revisit the framework, we talked about the database as a graph. These are kind of these graph templates with argmax and things like that. And this is a deterministic function of W and Z. And then Z given theta and X is just a log linear model. Okay. All right, so moving forward, we have to talk about how to train. And training means giving examples of X and Y, figure out what the parameters are. So a lot of work, in semantic parsing, kind of before this, worked on learning from examples of sentences and logical forms. And this, is fine, but this is generally, from an engineering point of view, this is actually not very good because how do you get this form of supervision? You have to ask people who know something about logic and linguistics to do this. And okay, I guess they don't get paid that much. You still need experts, aren't that many? But what we're going to actually try to do is learn from question and answer. So this is again the kind of behavioral view. And here, anyone who has like Google skills can answer these type of questions, and we can kind of scale up much more nicely. And also from I guess a scientific point of view, it's not reasonable to assume a model or a learning agent that actually gets exposed to these logical forms because where they come from. But it's very reasonable to assume that a child might get questions and answers. And I think you should also think more generally beyond question answering as an utterance associated with some external behavior. Like you could think about actions, someone picking up the chair. If I say pick up the chair and you see the chair getting picked up, then that's also a kind of signal for the semantics of pick up the chair. Okay, so the input to learning is a set of examples like this. You have the grammar and the features, and you can think about those as like innate or something. And you can, so the principle we use is maximum likelihood. I mean, if you want to do evasion, you can put a prior over theta and integrate out, but that's too expensive for us, so we just do this. And the principle here is that, what does this say? You should tweak the parameters, theta, which are the feature weights, to maximize the probability of getting the right answer given you got the question. So it seems like a pretty good principle. And for the algorithm, we use stochastic gradient descent or fancier versions of it, which basically look like pick up an example, compute the gradient, just take the derivative and take a step in the direction of the gradient. So actually very simple as and so something I guess I kind of omitted is that the set of logical forms is actually exponentially large. So we use theme search to prune, which means that every intermediate stage where we get a huge number of derivations, like 1,000, we just take the top 100 with the highest score and then throw the rest away. So it's possible that the ones we throw away might actually be useful later, but well. So here's a cartoon version of what we're doing here. So you're the learning algorithm. You pick up an example, where did Mozart actually press? And the answer is C is Vienna. And so you don't know what to press means because it's not a real word. But the algorithm is going to generate, using the grammar, a set of possible hypotheses. These are derivations which might be the right answer. And how do you know which one's the right answer? Well, you execute it and see what the answer is. And you can scratch out the ones which don't match the answer that you saw. And now notice that by learning from answers, there's actually ambiguity here. Not ambiguity in a sentence, but ambiguity in, let's not use the word ambiguity, uncertainty in the learning. So we don't know if it's place of death or place of marriage. So we go on and look at some other examples, do the same thing. And now over time, if the examples are kind of rich enough, you can see that the statistics kind of emerge. And what does to press mean? Okay, so.
But it couldn't have actually learned a brand new meaning for which there wasn't already a set of features in the database of answers, right? So either because there is, let's say to press was where did he first pick up a baton, right? And so that's not in your database of answers.
Yeah.
And it has to be something that means something that you already have a thing that it means, right? So be born, be die, be dead, be married.
Right. So so that's a great point. We're not going to learn anything that is not the world. And I didn't say this before, but the world is kind of fixed. And here, we're really focusing on only the language understanding, where you assume like perfect knowledge of the world. And if language refers outside the world, which it often actually does in that data set, then we just do the best that we can.
So to press could be a composition of things or not?
Yeah, so I didn't say much about what the features are. So one basic version of it is that to press just means a single predicate. But in later models, we actually relax the whole thing and say, well, to press could be any kind of weak subset of the relations. Because some things like, for example, let's just use the real world. Where did Mozart die, right? It's actually where and die that corresponds to place of death, not just die itself. So we're not being, composition is, like I said in the semantic parsing translation slide, composition is actually kind of nebulous in this particular task.
Do you have to look at the parameter values
Here?
Yeah.
Yeah, so the parameter values come in two places. When we're generating the set, we use parameter values to do beam search and prune. And also when we update the parameters, well, the parameter values obviously play in.
But it could be, let's say, some parameters are negative. So to press is you've got negative values on certain features. It's not just.
Oh yeah, the weights can be negative,
Yeah.
positive. The features can be negative or positive. The score can be negative, positive, but the probability is always positive.
You see that when you compute the gradients, it's on one data point, or it's on everything?
So it's on one data point because we're doing stochastic gradient descent, which means that we only, the way to think about it is that you randomly choose a data point and then you compute its gradient. And in expectation over this random choice, you actually get a gradient. Okay, so one thing that merits a little bit more attention is, I said, we need to pay attention to computation. I mean, in practice, we're going to have more than 3 derivations that we're considering. If we don't prune at all, we're going to get like a trillion or something. So think about in the beginning of learning, right? So all the parameter weights are 0. So you basically have a uniform distribution over everything. And so if you just like prune, then you're basically pruning randomly. And things that happen to show up at the top are just kind of random. And so you can think about this as really finding a needle in a haystack on long sentences. There's all these trillion derivations and maybe like 5 of them get the answer right. So in some sense, this should be like a hopeless situation. But something nice actually happens here, which is, and this is something that we didn't really plan for, but it just kind of happened, which is nice, is that here I'm displaying a bunch of examples and the set of derivations that make it to the top of parsing. And red means it was didn't get the answer right, and green means it did. So for most of the examples in the beginning, you're actually not able to get the answers right because you're just like randomly guessing. But there are very few examples, and these are examples typically the short sentences. Right? If I ask for like, what is the capital of France? I mean, there aren't that many ways to, even if you don't know what capital means, you can, but suppose you know what France means, then you can actually just generate all the possible relations from France, and then one of them is going to be capital. So, but what happens is that this is enough. So for these examples, you just skip, and for this example, you actually make the gradient updates, and now you know that effectively capital means capital in capital letters, and then and then what happens is that having better parameters allows you to do better search, and some other examples are now going to have things that maybe this is like what is the largest capital or something. So now it's easier to search this example, and now over time you actually see more and more examples kind of bubbling to the top. So, I mean, empirically, this is on a US geography data set. Over the number of training iterations, this is measuring how many, what fraction of the training examples you can actually get anything that reaches the answer. And this number is abysmal 25 and it goes to 100.
Yeah, so does this depend on the parameters being initialized to 0, or it seems like it wouldn't necessarily apply if they were initialized actually randomly, because then you do get a gradient, right? It just might not be the right one.
Yeah, so generally it's dangerous to initialize the parameters to large values if you don't know what's going on. I mean, we never really tried that because 0 seems very neutral place to start. I mean, people often in practice, they do bias, initialize some of the feature weights so that based on prior knowledge. Because we know some of the features are either positive or negative, so that helps, but we don't actually have to do that. Okay, so moving on, just a very quick taste of the empirical results. So we collected this data set. Here are the questions that are in this data set, and we're trying to answer these questions by looking at the previous graph. So here are some numbers. I mean, it's not maybe that interesting for you, but the red bars are our system. So we collected the data set in 2013, and there's been kind of steady progress. I mean, the numbers all, we've actually gotten 50% improvement, so that's not bad, but the numbers are still low because of some of it's because of the noise in the data set, and these are questions which real people type, so there's ambiguity, and then your point about questions not answerable in freebase, there's just a lot of kind of problems with that. So this is an example of a question the system gets right. Here's a question where the system doesn't understand what boarding school is, so it just ignores it. You get this set of schools. This is clearly wrong, and this one is right. And I was confused about this when I read George Washington. George Washington Carver did actually invent it, even though the sentence is unreliable. Okay, so that's what the system is. Questions?
Do you have a way to somewhat easily filter it out by what questions can be answered for a few days and then look at sort of what fraction of those you have?
Right. So this is actually we already filtered out. So we asked Amazon Mechanical Turkers to say, okay, if it can't be answered by freebase, like right, it can't be answered. But I guess they don't do a perfect job. Because I mean, the thing is that actually so many of these questions actually can't be answered by freebase, and I think the Turkers feel bad if they're just saying no to everything, so they just make something up. They're probably afraid if they say no, then we just like reject all their answers. Okay, so let me talk about a new project that we've been just doing, and here's this is work with my students, and here's the motivation: is that a lot of the queries that you might be interested in, like maybe you want to get the ACL 2014 papers, can't actually be answered by freebase, because freebase, despite its size, it has like a billion facts or something, but it's actually not very large. And then I guess maybe the more relevant way to think about this is, we're kind of assuming in freebase, in the case of freebase, that you have a world which is pristine and a pristine representation of what's going on. But in practice, what would be feeding this is like perception or something, and you're going to have noise and you're going to have things which don't really make sense. So you can think about what we're trying to do next is how to integrate cases where the data source or the kind of the world representation is actually not as clean. So as a kind of practical matter, if you want to answer these, if you go to Google search, you find these nice web pages. But if you wanted to actually understand language deeply by, if you have these queries like spicy dishes or papers about semantic parsing, then you're back to square one. These papers, these web pages don't actually answer that. But so the insight is to suppose that we've had this a web page with a table on it, and that's going to be our kind of noisy-ish representation of the world, and then we're going to try to answer hard questions. So here's an example of some of the questions that we're trying to tackle right now. So this is a table about I guess I don't know, I think it's swimmer or something. In a relay, in what city did Peter's last first place finish occur? And this would require looking at first places and looking at the last occurrence and looking at the city, which is Bangkok. So it involves sort of kind of navigating your way around. How long did it take this competitive finish at this particular date? So you look at, you have to look at this constraint, and figure out the time. And notice that how long did it take? It doesn't actually say how long it takes. It says notes. Okay, so you have to figure out that, well, maybe these look like time, so that's where did the competition immediately held before? So you have to understand what before and immediately means in this context, and so on. So we gathered a bunch of 22,000 questions and a bunch of tables, and we're really trying to do two things at once here. We're trying to tackle language which has pretty high logical complexity, so you can join, disjoin, use superlatives, comparatives, you can aggregate, you can use arithmetic, and so on. And we gathered this data set by asking Mechanical Turkers to write trivia questions about these web pages, and they were actually rather good at generating questions which are more compositional than your average questions. And the other challenge which I mentioned before is that these tables are just unnormalized. I mean, they're not completely crazy because these are all Wikipedia tables, but there's still quite a bit of variation in this schema. Okay, so, and okay, I guess this point is kind of interesting too. So if you think about a table as really representing like a particular context in which an utterance was said, we are going to try to have a set of training tables. So these are the contexts in which we see a bunch of sentences and which are distinct from the test tables. So this really tests the algorithm's ability to go out in the world to a new context, new table, and see if it can understand language in that setting. So the way we represent tables is as a graph. I'll just point out one interesting aspect, which is that I said these things are not normalized because if you see 1900, you don't necessarily know if that's like a number or a date. So we don't actually decide in terms of forming the graph. We just create auxiliary edges that capture the two possible interpretations. And then we leave it to the semantic parser to actually traverse one of these edges to produce the answer. Okay, so let's talk a little about parsing. So we don't actually see, as before, we don't see the logical form. But even if you saw the logical form, there's still kind of a gap here. Like the word Summer Olympics doesn't appear here, but you have country appearing down here, but it doesn't appear up there, and so on. So like I said, the classic rigid view of compositional semantics is really not applicable here. So what we're going to do, so if you think about our earlier mental model of how parsing works, you start with the words, and then for every subsequence, contiguous subsequence of words, you build a set of candidate derivations and you recurse. But that's going to be pretty inefficient if you have a lot of words which don't really map on nicely to your logical forms. So instead, what we do is something a little bit crazy, but the idea is that look at the candidates. There are certain words which we are very confident about, and maybe these are the words that like children have already. I mean, not Chicago, but like the basic lexicon, like nouns. And the idea is that these kind of are anchors which are going to drive the rest of parsing. So in particular, we assume that. I wish I had like better cognitive examples here, but pretend that Chicago is like something. So here, suppose you know what Chicago means. And I don't really know what the rest of this stuff is. So I could try to parse it, but that just doesn't make sense if I don't know anything. But what I do know, and this is like an important point, is that I know how Chicago can behave. I know Chicago is a city. I know it has properties like people were born there and so on. So I look at that and I try to build up the logical form from this kind of anchor without necessarily being anchored to the text. And this is kind of the strategy for building up logical forms when you don't necessarily have a lexicon that tells you what each of the words mean. So this is kind of an inverse process where parsing is very much driven by what you know about how the world works, rather than by how you believe language works. And so, this is just a way. Remember, the philosophy is we're just going to try to generate a set of candidate logical forms, and then we're going to try to learn. So what we do is define features on the predicates that we generated and the words that we saw in the utterance, and then try to learn associations. Like, if we saw this a bunch of times, we would hopefully learn that this is the location means lived, even though we didn't actually look up a lexical entry that says lived means that. Okay, so that I think is kind of probably a more generalizable insight about learning language in the context of it. So the results on this are as follows. So here is an algorithm that basically does very superficial matching and something in between, and then we have our model, which is 37.1, and so which is, I think substantially better here, but there's still a lot of room for improvement. One interesting thing I'll point out, and I already alluded this in the two-press example, is that often you can get the right answer for the wrong reason. So here is the correct logical form, which results in 2, but this is also the correct results in the correct answer, and so does this. And so often, because in the beginning stage of learning, you don't actually know what language means, so you're just trying to guess the logical form that gets the right answer, because that's the only thing you have to go on. So you can generate tons of things which are just wrong. I mean, the hope is that over time, like with the two-press example, you notice that, okay, these things, there's correlations between the words and the things that you generated to get the right answer, and you can hope to, sharpen your distribution around the correct logical forms. But, inevitably, because we don't have infinite data, some of our answers which we get right are for the wrong reasons, like about, let's say, like a quarter of them. So this is, I guess, maybe interesting from a language perspective. So here's the things that we get wrong. We don't know what consecutive means, and we're not able to generate the right logical form. We also don't know what same means. And maybe I guess make a point is that when we're kind of collecting this data naturally from people, we often see just a very long tail of different types of constructions that we might have not necessarily anticipated. Like we're already kind of trying to learn a lot in terms of all the lexical variation, but some of these words actually require more complicated concepts than we are generating right now. So we'd like to move to actually learning that like we would really like to learn like what does consecutive mean, and what does same mean. But that presents more computational challenges, because then we have to search over like a huge space of possible meanings for just a single word, not to mention composition. There's a bunch of table normalization issues which I won't bother with right now. Okay, so I guess just to refresh kind of the paradigm that we've been working in, we're talking about question and answering, but you should really think about this as some sort of as a kind of a language, someone who's understanding language. I get a piece of language coming in, but also think about this as encompassing the different contexts and maybe like gestures or whatever. And all of that, you can think about as just kind of noisy signals to access some sort of concept or a program, such that when your program kind of runs or executes, it actually has some behavior in the world. So maybe it's answering a question, maybe it's carrying out an action or so on. And what we're trying to do is to say I have observed only inputs and outputs. How can I infer these semantic representations? And really thinking about these as kind of a means to. Okay, so let me point out some ongoing work. How much time do I have?
I mean, almost 10 minutes.
Almost 10 minutes. Okay.
Yeah, use later.
Okay, so let me just try to quickly go through this. So we've been looking at various other parsing procedures using reinforcement learning to control the way parsing works. So right now we have this fixed procedure where we're saying, okay, parse this first, and so on. But intuitively, you should think about parsing things which are more promising first, and that might give you more information later. And we can think about this as a sequential decision-making problem, like a Markov decision process, where here's a state of a parser, and we're choosing an action which takes us to the parser state. And so this is actually pretty nice because it gives us a speed up. Let me actually skip this example. One thing that we're trying to do is also interpret high-level instructions like get the cup filled with water, microwave the cup. Here, individual words again mean quite complicated things. Like microwave is this kind of long sequence of move, open, cup in the microwave, close, and press. So this is, like kind of the consecutive examples where individual words actually have a lot of, okay, so this is our last slide. So I guess one interesting viewpoint is, we're trying to learn, we believe that there's interesting representations, in our heads that enable us to do certain things. And I'm trying to think as much as possible to kind of, from a learning perspective, let those semantic representations kind of fall out. Not because we put them in the first place, but kind of out of the pressure of having to do well on the task. And I think that's kind of satisfying because, we know the task is kind of the objective measure of like, okay, any system should be able to do this, and we can try to figure out what are the internal states that enable us to do that. One of the main challenges that we encountered is this mismatch between language and actually performing the task. So language is high level and the actions in the world are low level. And this is kind of something I've wondered about. To what extent can you actually learn everything kind of from behavior? I think you can learn quite a bit. I think you have to be a little bit more clever about what task this is really putting all the onus on what task you set up. But maybe this can reveal some insights into what is innate and what is actually learned. And we're doing language understanding, but this is kind of just the very beginning. There's two important aspects of language, which is the more context dependent and interactive nature of language, which we're not normally at all, but I think is important to the story. Okay, so I guess with that, I will conclude. Thanks. Questions? Yeah.
I was wondering if you could talk a bit more about the feature research you mentioned on the give me the cup or put the cup in the microwave slide.
Yeah, so very briefly, what we're trying to do right now is suppose you get text, you get a sequence of actions. Can you learn the meaning of the words that gives rise to this action sequence? And the actions are very low level, so what we do is try to represent the verbs in this sentence as post-conditions on what should happen, and let a planner connect the post-conditions with actual action sequence. And that kind of generalizes on that.
Is it like a virtual data set, 3D models? Or something?
Yeah, so we have a 3D simulator where we can go around and it has 3D positions that are still on. Yeah.
So, it seems like in the second part of the talk, there is a limited form of context dependence, but it's driven entirely by the fact that you have to do the task in different contexts, and so the information that's available to the system is different. But I take it that you mean in the in your concluding slide that the sort of context dependence that you're not getting that is potentially interesting is that something that's going on in these intermediate mappings and representations is context dependent. Am I getting that right? And so it's not that. So you might, the context of the system might just fall out of the fact that the system is in different contexts and it has different information, there's different affordances for the system in the environment. So do you have an intuition for the kind of for the way in which you think this sort of semantic parsing might show context dependence isn't entirely driven by
right? So
the
I
different
have
availability of the availability of different information, different structure.
I actually had a more specific thing I meant here, which is the context dependent on linguistic context dependence.
Oh,
If you have a sequence of sentences, you need to be able to. If I say it, then it needs to resolve to something in the context. And but also the idea is that in the second part of the talk, the context dependence was fairly limited because it was just a static snapshot. But what's interesting is that if you have time, now you're basically getting this set of graphs that evolve over time or something. And one of the things that we don't have a really good modeling solution for is that so context is by definition really big, and what part of that is actually relevant for your sentence interpretation. So when you have basic notions of salience, either in terms of time or in terms of space or in terms of importance, but how to kind of actually combine all those factors together is something that we haven't really looked at yet. Another interesting thing is even linguistically, so there's many forms of context dependence, like you say it refers to something. Sometimes you have ellipsis and that's kind of resolved. But also I think an afro of kind of actions, like if I say, put the chair on the table and I say, do the same thing with all those other ones or something, then you have to actually understand that to the extent that you have to resolve what all those other ones means and what is do the same thing.
Yeah. Maybe I can suggest an even more pernicious form of context dependence and the way that humans use language to do tasks, which is that people do these things. I don't know if you've heard of this, conceptual pacts, they call it. So if you and I are talking and we're trying to do a task, we will, throughout the course of the interaction, settle on certain terms that are maybe not standard terms, or they may start off as sort of descriptive things, but then they get shortened over the course of the interaction because we have sort of narrowed down the referring expressions we're going to use for things in the environment. And then you can people can move from one context to the next, and they come back, and when they come back to the interlocutor, they switch back into this mode of using these weird this weird mapping from things in the world to an actual lexical item. So that's a sort of, that seems on one hand powerful if you're thinking about it from the perspective of what human beings have to do, which is refer to things efficiently and effectively. But it seems like it might be really hard to do if data is generated by a system that's doing something like that, and you're trying to use it to train a system that isn't doing something like that. I don't know if you have thoughts or feelings.
Yeah, so that's actually a really interesting phenomenon. And currently our models can't really do this because it's not really learning on the fly. Like we learn a lot and we just apply it. So we've been actually thinking about the slide that I skipped is the first step at trying to be kind of more interactive. Don't look at this. I'll just say what it means. So we want to actually get into this mode where there's a dialogue. So the first part of this is actually the computer being actually be able to say, ask for kind of clarification. So what we have is, suppose the computer has some basic concepts, and you say, how do you say, the computer asks, how do you say Alice's parent whose gender is female or something, and then the user might say Alice's mother, and then the computer could say, how do you say parent of, mother of parent or something, that user would say grandmother. So we're imagining these kind of exchanges. It's maybe doesn't have quite the richness that you suggested, but I think it's a way to kind of adaptively grow the set of kind of lexical meanings that you can actually reference in the dialogue.
Noah was doing stuff like this with the, you heard of the wine machine?
Yeah, I've heard of that. Yeah.
Like the conceptual version of that.
Right. Yeah.
So what do you think about why your model was unable to learn concepts like same concept? Is it something about the expressive power of your grammar representation, or is it something about data?
It's so it's a good question. I don't think there's any conceptual barriers to learning this. I think certainly if we had more compute and more data, we could do it. So I think the main problem is that we actually, in order for this to finish in a reasonable time, we had to restrict the grammar So we don't generate like every single possible logical form. And as a result, we don't generate things that consecutive means. On the plus side is we also generate a bunch of things that are meaningless, but we can't generate everything. So I mean, in some sense, if you remember this picture back here, we're actually generating like a smaller circle. But we're working on trying to have a grammar that actually can generate a lot of more complex concepts. And also this involves probably changing the learning algorithm to be a little bit more strategic and adaptive rather than just like, here's a bunch of examples, just plow through them. So I think there's I'm pretty optimistic that we can do it, but it would just require a little bit more.
In your training from your model does not penalize complexity of the sentence. Right? The prior is flat, so you don't.
Well, I mean, it can and it cannot, depends on the learning. So we have features that measure the size of logical forms. And if it happens that a lot of logical forms are small logical forms suffices to get the right answer, then we'll learn that small logical forms are good. But it's not hard-coded as a supplier.
Yeah, so to go back to what you were, the slide that you skipped about having the computer ask some questions, I guess. There's a recent, as in 2 weeks ago, 1 week ago, graduate of the CS department, Walter II, who's been doing work on human-computer interaction. And he built this crowdsourced question answering system to help primarily disabled people, just to start it. If someone's blind and can't read the label of the package, they just have to pick it, they send it off to the crowd, get an answer. And sort of built this whole question answering system off of the dialogue with the crowd there. Okay. And one of his primary points was that if you take his data set and plug some automatic system in, something like this, that you get exactly that. You get training data for your system that's trying to predict these things, and at the same time, you get this system able to give feedback to the people, and you sort of include that in the meetings. Talking about that from the UCI.
Yeah, no, definitely that seems like, I'll look that up. The interactivity of kind of learning and actually kind of using the system is, I think, really the way forward in terms of scaling these up. And I think it's also much more realistic from a language perspective. Like children, they don't just sit in a room and learn a language and then they go out in the world and they're masters of it. It's much more incremental than that. And I think having a useful service to people is actually really good because then you actually get real users and real data.
Great.
Thanks.
Thanks.